Welcome back to Bite-Sized Breakthroughs. Today we're diving into a groundbreaking paper that tackles a major challenge in computer vision, open-world visual perception. Joining us is Dr. Paige Turner, the lead researcher on this project, and Professor Wid Spectrum, a renowned expert in the field. Paige, tell us about the paper and what problem it addresses.
Thanks, Alex. This paper introduces a new approach called Grounded SAM, which stands for Grounded Segment Anything Model. It's designed to tackle the problem of open-set segmentation, a crucial aspect of open-world visual perception. Basically, we want to be able to understand and interact with the real world in a way that's similar to how humans do. And that requires models that can accurately detect and segment objects, even if they've never seen those objects before.
That's a really complex problem, Paige. Can you give us some examples of where open-world visual perception is needed?
Absolutely. Think about self-driving cars. They need to be able to identify pedestrians, cars, traffic lights, and other objects in real time, even in unfamiliar environments. Or consider robots working in a warehouse. They need to be able to pick up and move objects they've never encountered before. These are just a few examples of how open-world visual perception is becoming increasingly important.
And this paper specifically tackles open-set segmentation, which is a core challenge in these applications. Professor Spectrum, can you expand on why this area is so critical?
Well, Alex, open set segmentation is about having a model that can segment any object or region in an image based on textual prompts. This is different from traditional segmentation models, which are trained on a fixed set of classes and struggle with objects outside their training data. For real-world applications, the ability to handle anything in a flexible way is absolutely essential. It's like having a universal tool that can be used for diverse tasks.
So, Paige, what are the key contributions of this paper? How does Grounded SAM differ from existing approaches?
The key innovation is that Grounded SAM combines two powerful pre-trained models, Grounding DINO, which excels at open-set object detection, and the Segment Anything model, SAM, which is fantastic at zero-shot segmentation. It leverages the strengths of both models in a complementary way. Grounding DINO takes in text prompts and generates bounding boxes around the objects described in the text. These boxes are then used as prompts for SAM, which can then produce precise segmentation masks for those objects.
That's a clever approach. It seems like a natural synergy between two very capable models. Professor Spectrum, what are your thoughts on the innovative aspects of this work?
I agree, Alex. The integration of Grounding DINO and SAM is a very elegant solution. It addresses a key weakness in previous approaches, which often relied on large language models to control and direct vision models. That approach could be quite limiting and inefficient. By directly combining expert models, Grounded SAM is more flexible and efficient.
It's fascinating how Grounded SAM can understand text and then accurately segment objects based on that text. But how does the model actually work? Can you walk us through the steps, Paige?
Sure. Let's say you give Grounded SAM an image and the text, "There are two dogs playing with a stick on the beach." First, Grounding DINO will analyze the text and try to locate objects matching dogs and stick in the image. It'll then output bounding boxes around those objects. These boxes then become prompts for SAM. SAM takes the image and the bounding boxes and generates highly detailed segmentation masks for the dogs and the stick, effectively cutting them out from the rest of the image.
So, it's a two-step process, with each model performing a specific task and building upon the output of the previous one. This makes sense, but how do you know that this approach actually works? What are the experimental results like, Paige?
We evaluated Grounded SAM on a benchmark called SegNW, which stands for Segmentation in the Wild. It's designed to assess zero-shot performance, meaning the model needs to segment objects it hasn't been explicitly trained on. We compared Grounded SAM to other leading methods, and it significantly outperformed them. In particular, the combination of Grounding DINO base and large model with SAM huge achieved a mean average precision of 48.7 on SegNW. This is significantly higher than methods like Unannexed, which achieved 42.1 mA, and OpenSeed, which reached 36.7 mA.
Wow, those are impressive results, Paige. It seems like Grounded SAM is truly a game changer in the field of open-set segmentation. Prof. Spectrum, can you comment on the significance of these results?
Absolutely, Alex. The fact that Grounded SAM surpasses existing unified models on this benchmark is a powerful indicator of its potential. It shows that combining specialized models can be much more effective than trying to train a single model to handle everything. This is a major shift in thinking about how we approach complex visual perception tasks.
But it's not just about segmentation, right? The paper also explores how Grounded SAM can be integrated with other models for a wider range of tasks. Can you elaborate on that, Paige?
You're right, Alex. The beauty of Grounded SAM is its versatility. We've demonstrated how it can be combined with other models to perform tasks like automatic image annotation, highly controlled image editing, and even promptable motion analysis. For instance, when combined with the Recognize Anything RAM model, Grounded SAM can automatically generate tags and annotations for images. And when integrated with Stable Diffusion, it allows for very precise image editing based on text prompts. We even showed how it can work with the OSX model for human pose estimation, enabling us to analyze specific human motions based on text prompts.
This is fascinating, Paige. It seems like the possibilities with Grounded SAM are endless. Prof. Spectrum, any thoughts on the potential impact of this model on various fields?
It's truly remarkable how this model can be adapted for diverse tasks. It has the potential to revolutionize various fields, including robotics, autonomous driving, content creation, and even medical imaging. Imagine a robot that can identify and manipulate objects based on text commands, or a self-driving car that can understand traffic signs and pedestrians in complex environments. The applications are truly boundless.
That's an incredible vision, Prof. Spectrum. But before we get too carried away, let's also acknowledge that there are limitations to this work, Paige. What are the key areas where Grounded SAM still needs improvement?
Of course, Alex. While Grounded SAM shows promising results, it's important to recognize its limitations. One area we're still working on is the accuracy of the generated annotations. While they are generally accurate, there can be instances where the model produces errors, particularly when dealing with very complex or ambiguous scenes. We're exploring ways to improve the robustness of the model by incorporating human feedback and refining the training process.
It's good to be realistic about those limitations, Paige. Prof. Spectrum, what are your thoughts on the future directions for this research?
I think there are a number of exciting areas to explore. One promising direction is integrating Grounded SAM with large language models, LLMs. This could create a powerful system where LLMs can control and direct Grounded SAM to perform complex vision tasks based on natural language instructions. Imagine being able to simply tell a computer, find the red car in this image and remove it, and have it seamlessly execute that task.
That would be revolutionary, Prof. Spectrum. It's clear that Grounded SAM is a significant contribution to the field of open-world visual perception. Paige, can you summarize the main takeaways from this paper for our listeners?
Sure, Alex. This paper introduces Grounded SAM, a novel approach to open-set segmentation that combines the strengths of Grounding DINO and the Segment Anything model, SAM. This approach effectively tackles the challenge of understanding and interacting with real-world environments by allowing models to segment any object based on textual input. The results on the SegNDU benchmark show that Grounded SAM significantly outperforms existing unified models, demonstrating the potential of combining specialized models for complex tasks. Moreover, its versatility in integrating with other models opens up exciting avenues for applications in various fields, including robotics, autonomous driving, content creation, and medical imaging. While there are limitations, particularly in terms of accuracy, the future directions for this research, such as integrating with LLMs, hold immense promise for advancing the field of open-world visual perception.
Thank you both for this insightful discussion. It's clear that Grounded SAM is a major breakthrough in the field of open-world visual perception, and we'll be following its development with great interest. Join us next time for another exciting episode of Bite-Sized Breakthroughs.